Hello students, welcome to this module 2 on our discussion on function spaces and eigenfunction expansions. In the last lecture we introduced the notion of how to expand a given function, a function in a given domain, let's say given domain a b, okay, where x belongs to a, x is in the range of a and b, between a and b, right? And we said that if you had an operator that is Hermitian in that domain, okay, and if you solve the eigenvalue problem for that LEI of x is for that Hermitian operator, and if f satisfies some boundary conditions, we discussed Dirichlet and Neumann boundary conditions and periodic boundary conditions in the last lecture, and if we ensure that EIs also satisfy the same BCs, that is both f and EIs, the eigenfunctions, satisfy the same BCs, okay, and these are lambda i's are the eigenvalues and EIs are the eigenfunctions. Then you can expand f of x as a series is some fi times ei of x, I going from 1 to infinity, where you have a large number of countably infinite number of discrete eigenvalues typically, and you can expand any function in terms of the eigenfunctions as the basis. This expansion is called Eigenfunction Expansion. This is a very general idea, and this is quite analogous to what we do in simple three-dimensional vectors, where I write a vector A in terms of AI, EI, where EIs are the three orthogonal unit vectors. Okay, so these are the coefficients here, and here these are the coefficients. These are the unit vectors in, let's say, Cartesian coordinates. Here these are the basis functions. The only additional complexity that you have to worry about are the boundary conditions in for functions, that the eigenfunctions and the function that you are trying to expand must necessarily satisfy the same boundary conditions. Okay, one of the special set of so this eigenfunction expansion is a general idea. One of the special cases of the eigenfunction expansion is called a Fourier series. What you do in Fourier series is the following. Here you take the Hermitian operator to be, let's say, minus d squared by dx squared, and solve its eigenvalue problem, and you find that sines and cosines are the eigenfunctions, and you have a whole bunch of them, right? And depending on the boundary conditions, let's say we take periodic boundary conditions, which means that f of x is if the domain is 0 and L, f of 0 is equal to f of L. Of course, you can have different domains. You could have domains between minus pi and pi and so on. Okay, right? Then you can expand any function in terms of sines and cosines. Okay. Now, just for the sake of concreteness, let's take the domain between minus pi and pi. Okay. Then the Fourier series becomes any function that is periodic in this domain. Okay, which is periodic with this wavelength, so to speak, is written as a naught by 2 plus summation k equal to 1 to infinity, okay, ak cos kx plus bk sin kx. This is called the Fourier series. Okay, this is the Fourier series of f of x. The periodic function f of x can be expressed in terms of sines and cosines, much like we expressed any vector in terms of the 3 unit vectors as a sum of 3 unit vectors and coefficients, right? It's in the same manner. The reason why there is a 2 here is because the domain is between minus pi and pi, and if you simply integrate this function without multiplying by sine or cosine, you will just get on the other side you will get a0 times 2 pi. The 2 will cancel. So this is a matter of convenience. This is not something that is very rigid. Whether you put the 2 or not, things will work out fine anyway, but you have to just be consistent once you fix a given Fourier series. Now these are called the Fourier coefficients, and AK, BK and A0 are called the Fourier coefficients. Okay, and how do you find them? Much like you find the coefficients of this expansion in 3D vectors. Suppose I say A is summation AI EI going from 1 to 3, then in order to find the coefficient AJ, you take the inner product of both sides with respect to EJ is summation I is 1 to 3 AI EJ EI. Now if it is an orthonormal basis, this is delta Ij, so this will become Aj is the inner product of Ej with A. In the same way, if you want to find the coefficients AK and BK, you have to take the inner product of the both sides with respect to the appropriate eigenfunctions. Okay, so AK is nothing but some inner product of f of x, inner product of cos kx with f of x, and if the eigenfunctions aren't normalized, you have to divide them with cos kx, the norm of the eigenfunction, the whole squared. If it is normalized, if the eigenfunction is normalized, this denominator will be unity anyway. Okay, but if they are not normalized, you have to write like this. Okay, now this becomes in integral form. The denominator is just 1 over pi. Okay, now this becomes minus pi to pi f of x cos kx dx. Okay, and similarly bk is 1 over pi minus pi to pi f of x sin kx dx. That is nothing but the inner product of sin kx f of x divided by modulus the norm of sin kx whole square. Okay, if the functions are already normalized, then the denominator will be 1. If they aren't, you have to just take whatever that value is. In this case, it is just pi. 1 over the denominator is just pi, so you have to just use whatever you get. So it's clear that the eigenfunction expansion, of which the Fourier series is a specific example, has a direct analogy with geometric vectors, wherein you can expand a vector A in terms of the basis vectors, or the unit vectors in 3-dimensional space. This is in the same way we are trying to expand any function in terms of infinity. Let's say n is equal to 1 to infinity f and en of x, where these are the eigenfunctions. In Fourier series, eigenfunctions are sines and cosines, but that's not always the case. You could have different eigenfunctions depending on the domain in which you're working, and so on. So there is a direct analogy with Fourier series, between Fourier series and the expression of a vector in geometric 3D space. Okay, so here the unit vectors are orthogonal. Here the eigenfunctions are orthogonal. Okay, so now the other key thing that you have to note down is that this infinity is only in theory. In practice, you may not use infinite number of terms. You may use n is equal to 1 to 10 or 50 or something. So in practice, we will truncate the number of terms in the eigenfunction expansion or Fourier series. Okay, we will truncate. We will not put infinity, obviously, we will put it to some finite number. Okay, now if you look at textbooks in Fourier series, you will get different expressions depending on the domain, normalization, and so on. If f of x is defined in the domain 0 to L, then f of x, the Fourier series will take the following form: a0 by 2 plus summation k is equal to 1 to infinity ak cos k pi 2 pi kx by L plus bk sine 2 pi kx by L, where k is 1, 2, 3 and so on. K is an integer. Okay, again you can find what are ak is using orthonormalities. So it is 2 by L 0 to L f of x cos 2 pi kx by L dx, and bk is nothing but 2 by L 0 to L f of x sine 2 pi kx upon L dx. Okay, so this is how you find the Fourier coefficients given the knowledge of the function. Now there is one thing that you have to note about Fourier series, and that's the following idea. The key idea about Fourier series is that you are trying to expand functions that are periodic in a given domain. So for example, you may have a function like this. Let's say defined between minus L and plus L. What this implicitly implies is that for every for every region between of period 2L, this pattern repeats. Okay, for every, just give me 1 minute. Okay, suppose if you were to expand this on the other side, then this will keep going like this. This will be between plus L and this will be plus 3L, and similarly it will also go in the minus direction. You will have between minus L and minus 3L and so on. So the Fourier series assumes that the functions are periodic over domain 2L here in this case, and it keeps repeating forever. Okay, so this is something that we have to remember. Fourier series is meant for periodic functions. Okay, now what about functions that aren't periodic? Right, that is something that we often encounter. So before I do that, let me also tell you or recap the exponential form of a Fourier series. The exponential form of a Fourier series is identical. You can either express in terms of sines and cosines, or using the Euler's formula you can write in terms of exponentials. K is equal to minus infinity to infinity ck e to the I. These are the eigenfunctions. These are the coefficients of expansion. Okay, so you can in fact call k pi by L as omega k. So you can write f of x is summation k is equal to minus infinity to infinity ck e to the I omega k x. Okay, this is another example of Fourier series in terms of exponentials. The key idea is that k goes all the way from minus infinity to plus infinity. Okay, now let's generalize Fourier series to functions that aren't periodic. Generalization of Fourier series to functions that aren't periodic. Okay, so this generalization is called a Fourier transform. Okay, the idea of a Fourier transform is rather simple. We say that suppose you have a Fourier series between 0 and suppose we have a function defined between 0 and t. So the time period so it keeps repeating after every t interval, right? The time period of this wave or this shape is t. Now if you extend t to infinity, okay, then this function becomes, and to be symmetric, you can also write it between minus t and plus t, okay. Now as t tends to infinity, this becomes an aperiodic function. Okay, so that is the trick that we are going to use to convert the Fourier series to include functions that aren't periodic, by pretending that the functions that aren't periodic are periodic with a time period t tending to infinity. So with this trick we will be able to find out what is called a Fourier transform. Okay, now let's call omega r as 2 pi by t times r. Okay, now we are going to look at the limit t going to infinity. Okay, so let's call omega r as delta times r, where this combination 2 pi by t is delta. Now as t tends to infinity, okay, suppose you ask the question what is omega r plus 1 minus omega r, that will be simply 2 pi by t times r plus 1 minus r, which is simply 2 pi by t. Okay, so delta omega, this is the change in omega, so delta omega is equal to 2 pi by t. As t goes to infinity, delta omega tends to 0. So you can think of omegas as the frequencies of oscillation. So as the time period t becomes infinity, the allowed frequencies of oscillation become a continuous variable. Okay, so and you will see that the summation in a Fourier series will become an integral. Okay, so let's recall how to find the coefficients. Suppose I say f of t is summation r is equal to minus infinity to infinity cr e to the 2 pi I r t by t. Okay, the coefficients cr are found as t by 2 f of t e to the minus 2 pi I r t by t dt. Now instead of 1 over t I can write delta w by 2 pi. Okay, 1 over t is equal to delta w by 2 pi. Yes, so we can write this as delta w by 2 pi minus t by 2 f of t Okay, f of t e to the minus I omega r t dt. So these are the Fourier coefficients. Now what I'm going to do is the following. I'm going to take the limit delta w goes to 0 as t goes to infinity. Okay, so f of t is summation r is equal to minus infinity to infinity cr e to the minus I omega r t. Okay, cr is nothing but what we have here. So cr is r is equal to minus infinity to infinity delta omega by 2 pi integral minus t over 2 to t over 2 f of t e to the minus I omega r t. Because I already have f of t here, I'll use a dummy variable here. Okay, so f of let's say zeta e to the minus I omega r zeta d zeta. This is basically cr, okay, times e to the minus I omega r t. Okay, so as t goes to infinity, this delta omega goes to 0. So the summation over this becomes an integral. So as t tends to infinity, delta omega tends to 0. Summation of r is minus infinity to infinity delta omega by 2 pi times any function g of omega r to the I omega r t is nothing but, you can take the limit of use the fundamental definition of an integral to convert this to an integral, which is 1 over 2 pi integral minus infinity to infinity, right? That's because r goes from minus infinity to plus infinity. We do not have okay, we do not have r anymore. Instead of r we have omega, right? And omega is nothing but omega r is r pi by L. So as r goes to infinity, omega also goes to infinity, right? That's why I have changed the summation to integral. In the limits of integration goes from minus infinity to plus infinity, right? Now this is d omega. The delta omega becomes d omega. This is g of omega e to the I omega t. Okay, so f of t therefore becomes integral minus infinity to infinity d omega. Instead of g of this is basically instead of g of omega, I have to put, see, this whole thing is let me just back up here. So we have substituted what is cr, right? And in general, if you had a function, this should be a function of omega, because we have integrated over zeta, so this will be a function of omega. So instead of that, you have this whole thing here, right? You have this whole minus infinity. Again, t goes to infinity, so this is f of zeta e to the minus I omega zeta d zeta, right? This is exactly what we had here for g of omega times e to the I omega r t. Okay, so basically what I'm saying is, instead of g of omega, I substitute this, okay, and rest remain the same. Now by analogy, this is the function f, okay, of t, and instead of Fourier series summation, you have a Fourier integral. Instead of the Fourier coefficients, previously we had Fourier coefficients CR in the Fourier series expansion, okay, CK. Now they become functions of omega. Okay, so this is called the Fourier transform f cap of omega or f tilde of omega, depending on which book you follow. Okay, so this becomes f of t is therefore minus infinity to infinity d omega f of omega e to the I omega r t. Okay, so this one is called the Fourier this is, Fourier transform comes in a pair. You have to tell how, given f of omega, how f of t is found, and likewise given f of t, how f of omega is found, or f tilde of omega is found. So this one is written as, right, okay, I'm sorry, I've perhaps missed a factor of 1 over 2 pi here, right? So I will have to write 1 over 2 pi. This 1 over 2 pi has to be written here, right? So f of t is 1 over 2 pi. Okay, and f of omega is minus infinity to infinity du f of u so this is f of omega. Okay, the Fourier transform of f of t is denoted as f tilde of omega. Sometimes some textbooks don't even write the tilde or hat, and they simply write f of omega, with the meaning being implicitly understood. Now the factor of 2 pi, in some textbooks you will find that both will have a factor of root 2 pi, so that it's still equivalent, they are still equivalent. And f tilde of omega is 1 over root 2 pi okay. So this is called the Fourier transform pair. Okay, so this tells you, given f of t, how to find f tilde of omega, and given f tilde of omega, how to find f of t. Okay, now let's so Fourier series is Fourier transforms are very useful for the simple reason. So let's first tell you what the use of Fourier transform is. Suppose I say f of x is 1 by root 2 pi integral minus infinity to infinity d omega suppose I write like this, right? This is the Fourier transform, this is the inverse transform. Given f of omega, how to find f of x. Now I'll calculate df dx from here, 1 by root 2 pi. Now the boundaries of the integral are constant in some sense, so d omega, and f tilde of omega is independent of x, so it will appear as such. Let's see, t, not x, right, with respect to time, I omega. So this is nothing but df by dt is 1 over root 2 pi infinity to infinity minus infinity to infinity times I omega times f of omega e to the I omega t. Okay, now if I just worry about this function here, okay, this must be the Fourier transform of df dt, because the Fourier transform of any function is 1 over root 2 pi minus infinity infinity d omega times something times e to the I omega t. Okay, so the inverse transform, or in other way around, this stuff in the square bracket must be the Fourier transform of df dt, because if I simply had f and then instead of I omega f you simply have f tilde, we identified f tilde as the Fourier transform of f, but now we have df dt, so the Fourier transform of df dt is I omega times f omega. Okay, this is very helpful in solving differential equations, ODEs and PDEs. The key thing to note is that the derivative with respect to time has now become a multiplication with respect to this omega variable. Similarly, I can write d squared f by dt squared is I omega squared f of omega, and so on. So this already renders a great simplification when by converting differentials into algebraic expressions. This is one of the major advantages of using Fourier transform. Okay, now I'll work out an example. I'll say find the Fourier transform of f of t is equal to 0 for t less than 0 is equal to a e to the minus lambda t for t greater than 0 and lambda is greater than 0. Okay, so what is the Fourier transform f tilde of omega? 1 by root 2 pi minus infinity to 0. You have to split because the function takes two different values, times 0 times e to the minus I omega t dt plus a by root 2 pi 0 to infinity e to the minus lambda t e to the minus I omega t dt. Now this is 0 because of this, right? So f of omega, after you integrate this, you will find that it is simply a by root 2 pi times lambda plus I omega. Okay, and if you want to find out whether it is indeed correct, you can invert the Fourier transform. Okay, so f of t is 1 by root 2 pi, right, times infinity a by root 2 pi 1 by lambda plus I omega okay. So f of t is 1 by, now there are two root 2 pi, so 1 by 2 pi integral minus infinity to infinity. Now this is a by omega d omega. Okay, now this appears like a complex valued integral, so we can use residue theorem. So we'll write f of t as 1 over 2 pi integral minus infinity to infinity a omega plus lambda by I e to the I omega t d omega. Now this has a pole. If I take a contour between minus r and plus r and take a semicircular contour in the positive where for y imaginary part greater than 0, then this is cross counterclockwise path, right? Now there is only one of the pole that is present within the domain of the region, right? And okay, I'm sorry, this can be also be written as 1 by 2 pi integral minus infinity to infinity a by omega minus I lambda, but I'll also pull out a factor of I. Now this integral, and of course you have e to the I omega t d omega. There is a pole at z is equal to I, and there is a simple pole at omega is equal to I again here, I lambda, right? So what we have to do, simple pole omega is equal to I lambda, right? So the integral is nothing but f of t is a by 2 pi I minus infinity to infinity okay. So when you evaluate the pole at omega is equal to I lambda and use the residue theorem, f of t is a by 2 pi I times 2 pi I. We are now evaluating only this integral. Okay, this is using residue theorem. Okay, now a by 2 pi I times 2 pi I times sum of the residues, but there is only one residue. So this is residue at omega is equal to I lambda. Now what you do is you multiply the whole equation by omega minus I lambda and take that limit as omega equal to I lambda. You will find that this f of t becomes, and the 2 pi I from this 2 pi I cancels with this, so this is a e to the I lambda t, because you had already an I here, and omega is equal to I lambda at the pole, right? So this is nothing but a e to the minus lambda t. Okay, so this is again verified because we started off with this in the previous so you had a e to the minus lambda t, and that's what we finally get after taking the inverse transform of this function. Okay, so now what I will do next is to explain a couple of concepts using what is called the Dirac delta function. The Dirac delta function is defined such that integral a to b, integral, let's say, minus L to plus L delta t minus a dt is 1. Okay, this is the definition of Dirac delta function, and delta of t is equal to delta of minus t, delta of at is equal to 1 by a delta of t, and so on. Okay, these are the general properties of the Dirac delta function. Now, what is the advantage of Dirac delta function? If you take any function and then you multiply it with the Dirac delta function, you will get the answer evaluated, or the answer for this integral is the function evaluated at the pole, at the simple pole. So this is a very, very useful result in terms of understanding Dirac delta function. Okay, so if you think of a Dirac delta function, it will be like this. It will be a spike, and as you make the spike smaller, as you make the width smaller and smaller, the height will rise. Okay, and it will be a as you make the width smaller and smaller, the height will continue to start rising. It will appear like a very, very strongly peaked function. Okay, so the other property of delta function is delta of t is equal to delta of minus t, delta of at is equal to 1 by mod a delta of t, and so on. Okay, these are some of the useful identities involving the Dirac delta function, which will find it useful. Okay, so now so what is the advantage again of Fourier or Laplace transforms? That you are able to convert PDEs to ODEs, and thereby simplifying the problem of solution of PDEs by simply solving the ODEs. Okay, I'll stop here, and we will start from the next lecture, which is based on Laplace transform.